Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
We're honored today to have Nathan Eagle visiting us and sharing some very exciting work and exciting data collection and analysis going on that he's leading up. Nathan is a research scientist at MIT and a postdoctoral fellow at the Santa Fe Institute. He's been applying machine learning and graph theoretic analysis, graph analysis, to understanding from massive data sets, particularly mobile phone and landline phone communications data, insights about human behavior and related phenomena. For example, disease processes. He's been getting into these days. Nathan was a Fulbright scholar in 2006, where he, went off to Kenya and Ethiopia and spent time working in the mobile phone space. In fact, developing educational curricula. Had to program mobile phones that's now being taught widely throughout Africa. He did his bachelor's and master's at Stanford, his PhD at MIT, and he's working on founding a kind of a new area of work we've been referring to as AID, artificial intelligence, learning and reasoning for development, kind of subfield and an active subfield, probably one of the more exciting subfields of IC for D, information and communication technology. I say ICT for D, communication technology for development. So with that, we'll hear from Nathan today about investigation of complex social systems from communication data, from hundreds to thousands to millions and soon to billions of nodes and their links amongst one another. Thanks.
Thanks, Eric. So it's a pleasure being here. Maybe a little bit more background about kind of where I'm coming from. So I joined Sandy Pentland, the Wearable Computing Group with Sumit Basu and others back in 2001. And back then, wearable computing really meant strapping computer literally to your back, and occasionally you'd see guys with head-mounted displays on their heads, and they'd be walking around MIT or Boston capturing really interesting data about themselves and about their environment, but sometimes much to the amusement of the other people who are watching them walk around MIT and Boston. And so I was, there was at least a trajectory where I would be basically strapping a computer to myself and collecting similar types of data. But this was 2001, 2002, and this was kind of converged when Nokia launched their first mainstream programmable phone. And so instead of going down that wearable computing route, it started hacking on phones. And I've been basically programming phones ever since. Finished up my PhD and had started a small company that essentially connected socially awkward singles in Manhattan together based on their mobile phones. And I felt like there's something more. Like what I really wanted to do is build an application that had a massive impact, and that this impact just wasn't happening in the States or Finland or Korea for that matter. But in 2005, 2006, things were really kicking off in Africa. And so I was lucky enough to get a research scientist position at MIT, but instead of having my office in Boston, I lived in a small village out on the coast of Kenya, a village called Kilifi. And there I did a variety of different things that Eric alluded to, starting this kind of mobile phone programming curriculum originally at the University of Nairobi, but it's now being taught in 10 sub-Saharan African countries. And literally thousands of African computer scientists have gone through this program and learned how to program phones, which has resulted in hundreds of applications designed specifically for the African market, and quite a few startups based in Nairobi and Addis Ababa and elsewhere. And one such startup is my own. It's a company based in Nairobi called TextEagle, and it enables mobile phone subscribers to earn small amounts of money on their phone by completing simple tasks for corporations who pay them either in airtime or M-Pesa, which is the local mobile money. This was just really kind of a pipe dream this time last year, but it's now a working product across East Africa. And the reason why it happened so quickly is because I've got fairly strong connections with, well, literally every mobile phone operator in East Africa and dozens around the world. And so those relationships are going to be what enables a lot of the analysis you see at the latter half of this talk, when I'm talking about scaling to millions and tens of millions, and soon I hope to have a data set that involves over 1 billion people by this time next year. So that's a little bit about who I am, and now I'm going to kind of talk now a little kind of overview of what this talk's going to go into, and it's going to be on scales of magnitude. So we're going to start off with what I did in my doctoral research, where we studied 100 people and were able to start inferring the social relationships between people based on behavioral data. And then I'm going to talk about how that study scaled to 1,000 people. We did the same thing, but now this is 1,000 people working in 2 office buildings in Helsinki. From 1,000 people, I'll talk about a data set that we have collected with a company, IMMI, where this is now 10,000 random sample people across America, where again it's the same type of Uber spyware that's installed on their phone that I'll go into detail about. From 10,000 to 100,000 criminals in Philadelphia, and talking about things like whether or not a crime wave exists, and if a crime wave does exist, can we quantify it in terms of its magnitude and its speed?
That seems very, very good.
This is what happens if you do a Google image search for criminal. The other image shows is Bill Gates and his photo. Yeah. From 100,000 criminals, I'm going to be talking about the 1 million mobile phone subscribers in Rwanda. And the questions that we're addressing there are things like, how does this urbanization affect people's social support groups and the dynamics of things like slums? As Eric alluded to, looking at disease and patterns of disease and see if we can start seeing, is there kind of a behavioral signature associated with an outbreak of a disease in a particular region that gets reflected in the CDR, the call data records. From 1 million, I'm going to go to the 10 million mobile phone subscribers in Kenya, and this is a particular data set that's I find fascinating because it's not just communication anymore, and it's not just people's movements, but now in Kenya, people can send and receive money on their phones, and so we now have this flow of actually economic resources throughout the country that is fascinating to study. From the 10 million Kenyans, we're going to go into 100 million people in the UK, and this is now in collaboration with British Telecom and the civil service in the UK, where we're coupling just about every phone call made in the country, both landline and mobile, with things like socioeconomic status data, access to healthcare, education levels, average income, and trying to figure out, basically trying to establish causality. Like, are there signatures associated with wealth that are indicative, again, within the call data records? And then lastly, what does it mean when we start comparing this data across cultures, across continents? What kind of new research questions can be addressed when N gets inevitably to the level of billions, which it will in the very near future? Okay, so that's kind of an outline of the talk. For people who are familiar with social network analysis, these 2 graphs, that one in particular, should be fairly familiar. These are the graph on the top was collected back in the 30s by 2 guys, Roethlisberger and Dixon, and this is a graph where these are social networks. So the nodes are people, and you have an edge in this case on the top graph if you were seen playing cards with another person in this particular electric company which is being studied. And so that's one social network, and this is a social network that was recorded maybe 40 years later, back in the 70s, and this is the famous or infamous, really, Zachary Karate Club data. And there's been a lot of people, a lot of my friends and peers and people who are, much smarter than I am, who have dedicated a large fraction of their lives to studying this particular graph. The Zachary Karate Club data has been in literally hundreds of physics journals where people are trying to look at graph segmentation, trying to pull out community structure. And so while social network analysis is kind of has veered well beyond social sciences to statisticians to physicists, and yet generally when you read these papers, they're really only for kind of the papers have algorithms that are only applicable for small and static graphs. Despite the fact that we are now inundated with behavioral data that's many orders of magnitude larger than these types of graphs. Originally from the internet, but now just from everyday life. And so a lot of the projects that I'm going to be overviewing come from problems. They come from people who need help, and those people are anyone from the police chief in Philadelphia, urban planners in Kigali, epidemiologists in Kenya, the civil service in the UK. All these individuals are practitioners who suddenly found themselves inundated with data, and they're looking to the academic community for help, and are understandably a little bit confused why there's so many brilliant people focused on a particular karate club from over 30 years ago, when in reality there's the data that we have. The data that these guys have is just much richer and much, in my opinion, more interesting. But the problem is it's not small, it's not static, it's not computationally tractable. And so fundamentally, we need a new set of tools to deal with data that we currently have today. Things like betweenness centrality. These are metrics these are fairly interesting and sophisticated metrics that can characterize, in centrality, for example, how many shortest paths go between, through a single node. But something like betweenness centrality is more or less intractable for any of the type of data that I work with. And so what I'm trying to push for is come up with these types of analogs that can do better at analyzing what we have and what we need. So the real focus here is going to be shifting from just thinking about theory and thinking about building a generative model that can mimic a particular degree distribution, and going towards really focusing on outcomes. So trying to understand what is it the process that we want to get a better handle on. And outcomes of interest for me are things like disease. There are things like traffic jams. There's things like access to healthcare. And all these outcomes of interest are basically can be informed by and conditioned on the petascale data that we currently have. But it is fundamentally two different philosophies. I'm coming at it from the outcomes perspective rather than looking at the data for the data's sake. And that's how I at least try to differentiate some of this particular work. And also I don't want to be misunderstood. I mean, a lot of the results here do come from collaborations, a long series of collaborations with academics ranging from social scientists to particle physicists, and where we do try to validate theory and come up with better theory about the dynamics of complex social systems. But for me, I think the harder question here really is, once you've got all this data and once you fit a particular distribution, how can we start using this data to improve people's lives? How can we make the society of that, wherever this data is coming from, how can we make that society better? And that's kind of going to be an underlying theme in a lot of the work that I'm going to be talking about. So with that as a long-winded introduction, let me start on the first order of magnitude here, where this is n equals 100. And these are individuals who are subjects in this original study, where we gave out phones that had more or less uber spyware on it. And it started on boot. It was invisible to the end user, and it literally logged everything. Logged communication, logged proximity, logged location. And what you can do with this type of data is some fairly interesting human modeling. So given the fact that subject 104 is on their way to Central Square, and it's 3 p.m. on a Tuesday, can we predict where this person's going to have dinner? Can we predict where this person's going to, who this person's going to have dinner with? Given the proximity patterns of S22 and S18, if they're proximate by the coffee machine at the Media Lab every Tuesday afternoon, that corresponds to one type of relationship. But if they're proximate on downtown Boston late on Saturday night at 3 in the morning, every single Saturday night, it's a very different type of relationship. And then lastly, looking at the aggregate behavior, you can start seeing things like the onset of, for example, MIT Finals Week by people moving faster. Or we were capturing data when the Red Sox won the World Series for the first time. And then suddenly all the models broke. Everyone became unpredictable. And what happened was like the majority of the subjects went into downtown Boston. And there was a big rally down there. And the urban planners, they were interested in looking at how people dispersed from that particular gathering point. How many people took the subway? How many people walked over the bridge? How many people rode their bikes? With this type of data, we can start answering questions about how people utilize urban infrastructure. And so that's kind of a bit of a broad overview of this type of data set. Was there a question?
So you said the spyware was invisible. So just this is a general question for all your data.
Yeah. Is this a privacy question?
Did the subjects know they were subjects?
Oh, absolutely. I mean, so I've to do this study. I mean, we can tell who's sleeping with whom, right? Right. I mean, so there's a massive amount of intrusion in terms of privacy. You would never be able to do this, at least in an academic context, without signing a massive consent form. Absolutely.
So then hawthorne effect comes in, right? If they know that you're being noticed, they'll behave slightly differently.
That people were. I mean, and I was concerned about that as well. And if you saw the first week of behavior, it does deviate significantly from the rest of the behavior. But what you can see is that people basically kind of slip into a routine, like basically follow a routine. Whether or not that's a routine that's influenced by the fact that they know that they have spyware on their phones, it very well might be. But I think that it's that first week where they got nervous and then they forget about it.
And I'm just curious to see if that first week scales to like different, like as n increases, does that number change from? I'm just looking
I think it really depends on the demographic, right?
Okay.
So in the next data set I'm going to be talking about, these are individuals who work for a large Finnish cell phone manufacturer, and these guys, they're so used to participating in these types of studies, where I think that it'd be even less. But at the end of the day, it's hard to answer that question for obvious reasons. One of the things that I've been trying to push with very minimal success is this idea of characterizing an individual or a demographic with this notion of entropy. So this idea of how much structure is in their behavior, how much information, how much randomness. So this idea of information entropy is how much information is in a particular time series in this case. So this is an example of an individual who's a low entropy person, meaning this is the white spots is him at home, then he's at work, and then he's back home again. His day-to-day structure is dictated by dropping off his kids and picking them up to and from school. Whereas this was an individual who actually was my office mate at the time, who's a grad student. He's just as likely to be in the office at 3 a.m. as 3 p.m. So you'd have to really squint to see much structure here. So high entropy, low entropy, and it should be pretty obvious then that when we're starting to parameterize individuals in terms of their behavior, in terms of predicting what they're going to do next, we can do a lot better on the low entropy people. You can see the patterns. You can figure out. You can get a pretty good guess when he's going to show up to work the next day. Whereas the higher entropy, it's a bit trickier. And then you can start characterizing demographics this way too. So we gave out phones to these 18-year-olds who just arrived on campus. The business school students, admin staff, and and again, it's not particularly surprising, but it's the freshmen that are the most entropic. And we also had one other subject that I ended up throwing out, and I'll talk about him a little bit more in detail later. But he was off the charts in terms of entropy. He was well beyond 50, and this is Marvin Minsky. And I threw him out because he was messing up everything, and I figured that he was such an outlier that it didn't matter. I'll talk a little bit later about how we're discovering these individuals across different demographics who are extremely high, very entropic. And it makes me kind of reconsider throwing him out of the data set.
So the different ways to define entropy with location would be visits place of type X within time horizon T. Exact same place.
Yeah.
Within a larger time horizon, but defining the different constraints on how you define sameness, you might get different scores for different kinds of analyses.
That's totally true. And in this case, this is broken down on hourly windows, and place in this context is things like home, work, elsewhere, that sort of thing. But depending on how you structure it, you can get, I'm sure, radically different entropy scores. But the point originally was just simply like, get a single metric and try to quantify how much structure is in someone's life. And then once you do that, one of the things that you can start doing is trying to model a particular, every single day. And in this case, what we're doing is you can think of every day in a subject's life as a single point in a really high-dimensional space, right? And the point, one of the issues is that we don't live our lives as random number generators, but rather these points they're not randomly distributed through that high-dimensional space, but they're clustered. And so if you just do a simple dimensionality reduction on this, you can actually start pulling out what the principal components, or we're calling these eigenbehaviors, because my advisor at the time, created this eigenface literature, and so this is using it more or less like the identical technique, but trying to quantify these salient behaviors associated with individuals' lives. And you
computed, so the PCA was on n individuals.
Yeah. So you can basically, we get a matrix of this time series,
right.
and this is, we're just taking the eigendecomposition of the covariance matrix of that.
So you're doing a separate decomposition for every person.
That's correct. And then 2 slides later, I'll show we changed that.
Okay.
Yeah. But I just wanted, this is something that kind of pulls out some obvious things where you can start looking at how many eigenbehaviors you need, how many of these vectors do you need to recreate someone's day. And so for low entropy subjects, you don't need very many, whereas in higher entropy subjects, you do to get the same type of accuracy. But then to Sumit's point, so originally this was just for a single, each day was a particular point. But now you could start characterizing individuals as a single point in a very high dimensional space. And then characterize demographics. So this is for a kind of a toy example, but you can. In this case, what we're doing is trying to quantify the Sloan Business School behavior space. So collapsing all the business school students down and trying to quantify their behavior on in this case a 2D, so with 2 vectors. And then what we would do is we would just try to figure out whether or not someone's a business school student by measuring their Euclidean distance between that space and where they lie. And we got something like over 90% accuracy in terms of differentiating business school students. All right, so that's looking at kind of on an individual level. And now I'm going to talk about dyads, so pairs of people. And this is a graph here of basically proximity over the course of a day. And this is the friendship graph. So the research challenge is trying to figure out how do you winnow down the edges in this particular graph to get at what the underlying friendship graph is. And I'll be kind of approaching this problem from a lot of angles, whether this is proximity, in this case via Bluetooth, or the operators have a lot of communication data. So trying to figure out, so what the operators have is this massive communication graph, and what they want to get at is a social network. So trying to look at a social network through the lens of proximity or through the lens of communication and get at what the underlying relationships are is an important question. What we've been able to get, though, is much richer data than just operators have. I mean, we can think about a graph that has multidimensional edges. One type of edge could be things like whether you're proximate on Saturday nights. Another type of edge could be, are you proximate at that person's house? Another edge would be communication. So we've got this graph, this social network, with lots of different types of edges. And the challenge here is trying to infer where are the friends? Can we infer the topology of the friendship graph based on all these higher dimensional edges? And it turns out you can pretty trivially. I mean, this is my collaborator likes to call this the relationship EKG. There's probably a better name for it, but I haven't come up with it. But this is probability of proximity at MIT in this case, and then off campus. And there's 3 different relationship types, right? There's if I'm friends with Mike, or if I say I'm friends with Mike and Mike says he's friends with me, that's reciprocal. That's green. If I say I'm friends with Mike, but Mike says he's not friends with me, that's an asymmetric relationship. And then, of course, there's the symmetric non-friends. And what we're finding is that this asymmetric friendships are generally when you're really proximate a lot at work. Meaning, if you're working with Mike a lot, you may assume that you guys are friends, but Mike may not think that you are. But if you look at proximity on Saturday nights, for example, you get a much more if you're proximate on Saturday nights off campus, especially, you're much more likely to be friends. And so we can get something like a 96% accuracy in terms of inferring the edges of the friendship network. But we can do a little bit. I think what we can do is a little bit better, because the survey traditionally was just mark off the people you're friends with, yes or no. What we can recreate is an actual weight associated with the relationship, where that weight is characterized by how much time you spent having dinner with that person, at that person's house, having lunch, traveling with the person, communicating over the phone, et cetera. And so I think we can get a much kind of richer depiction of what the true relationship is. And what's nice about, this is going to be coming out in PNAS, I think, in a month and a half. What's nice about this particular technique is that we're able to kind of scale traditional social network analysis to a much larger group of people, potentially. Meaning, so we had to kind of get ground truth, and so we had to have people go through a survey where they read all 100 names off and had to check the names that they were friends with. That obviously just won't scale as you want to increase your sample size. You're not going to be able to get people to do that for 1,000 people or 10,000 people or the 100 million people that I'll be talking about at the end. And so you need another system to be able to kind of quantify what the social network is without having to deal with these types of surveys. All right, so now from 100 MIT students, we're going to 1,000 individuals who are living in Helsinki. And what we've done here is we basically put the same Uber spyware on all of their phones. And we did one more really obnoxious thing. Every 20 calls they make, we have a little survey that pops up and asks them to label the relationship. Is this person a friend? Is this person an office worker, an acquaintance, a colleague, no relationship? This is the won't disclose pattern. So this is just the temporal pattern, like the temporal distribution of when individuals make calls to what type of relationship. And so we not only have the temporal, but we also have the location where those calls were made. Yeah.
That's all making calls, not any call.
This is making calls. Yeah, we had the survey only go when you make a call. But again, this kind of leads us into this problem that the operators have, right? Where they've got all this communication data, and they really want to get at relationship. And the operators have come up with sneaky ways of getting at that, right? You've heard of like the friends and family plan, or the FAV5, or whatever that T-Mobile is pushing. Like they're trying to get access to this type of data from you. And what we're trying to do is build a little classifier to see if there are kind of discrete signatures associated with these types of relationships. So from 1,000 Finns, now this is 10,000 random sampled individuals across America. And the real key component here is this is random sample. So this is through collaboration with IMMI. What IMMI did that original reality mining study, so that Uber spyware on people's phones, but they used one additional sensor that I wasn't allowed to use due to CUI's constraints, as well as the fact that I don't think anyone would sign up for it, or else I didn't at the time. And that sensor is the microphone. So they're turning the microphone on these phones for 10 seconds every minute and recording the ambient audio, pushing it back to a server. So have you guys heard of that Shazam? Like there's these companies where you hold up the phone to the radio and you get a text message back about what the song's being played. So the guy who started that company came out, he did his PhD, I think he finished it about 10 years ago. It started a couple companies that were basically doing this acoustic matching. Both in Europe and here in the States. This is his latest company. And he's found that this, I think they just finished closing a $50 million round from Draper. Nielsen is trying to hostily acquire them. Like they're a hot commodity. And the reason why they're a hot commodity is because his algorithm not only lets you figure out what song's being played, but what advertising you're being exposed to. And so you can actually get a much better sense of whether, what media people are consuming, what TV show you're watching, what movie you're watching, what radio station you're listening to in the car. And what's the really cool thing, I think, well, one of the really cool things is that they're able to show kind of marketing efficacy. So if you've watched the co-branded Burger King Simpsons ad, you're actually much more likely to go into the Simpsons movie. Like they can make these types of claims now, and they can make them because this is 10,000 randomly sampled individuals. And one of the major critiques with the earlier work that I've talked about is that, okay, so you've parameterized the lives of 100 MIT students. So what, right? Like, how does that scale to the population at large? Suddenly, we're able to start talking now about, well, basically about the patterns of, much more generalizable patterns about demographics. So not just MIT freshmen, but we can say now that the most entropic group that we found in these 100,000 people turn out to be women under 30 who are making more than $60,000 and are college educated. Like, these are now claims that we can make because we have a random sample. So from 10,000 random sampled individuals across America, this is now 100,000 criminals. So a red car corresponds to a carjacking. The little circle corresponds to a graffiti event. The martini glass is public drunkenness. Let's see, the RX symbol is a drug bust. So what we're trying to do here, the research question is crime contagious? Is there such a thing as a crime wave? And originally, when I wrote the little script that would plot these things as a time series, I was hoping to start seeing kind of spread over something like a lattice, but it's clearly a bit more noisy than anticipated. And so this is a project going on with a student of mine and an epidemiologist from UPenn, trying to get at answering this question. But there's been in the past, a lot of literature on things like, is obesity contagious? Is smoking contagious? And using a similar technique, actually, I think it was the New England Journal of Medicine recently, there was a paper where they showed that height was contagious and acne was contagious. So you have to be really careful when you're talking about contagion over a social network when there's things as homophily, this idea of birds of a feather flocking together. And so disambiguating, like what is homophily and what is an actual contagion. Well, for me, it turned out it was a lot harder problem than I anticipated. So, anyways, that's my 100,000, and now I'm going to launch into CDR. So CDR stands for call data records. It's the data that mobile operators capture about their subscribers. And just to make sure that everyone's on the same page, this data it's far richer than just a communication graph. I mean, well, we've got things like the caller and the receiver. We've got the time and the duration of the call, the cell tower that's associated with the call. And in this data set, we've got 4 years of data. And this is data from the only telecommunication company in the country. So this represents every phone call made in the country over 4 years. And so what that enables you to do is ask some really interesting questions about how society in general is evolving over time. We've got things like me-to-you airtime transfer, so you can actually send and receive airtime on these handsets, and that's being done on average about 4 times a month per subscriber. You've got individual, so not only do you have kind of these multi-dimensional edges, where edges could be sending a text message, making a phone call, sending airtime, but you've also got a bunch of attributes for the nodes. We know what phones people are using. We know what region they're calling. We know scratch card denomination. Eric and I were talking about this earlier today. So all these markets, or at least most of the markets that I am involved in, are generally prepaid. So that most of the world has prepaid markets where you buy a scratch card and you can buy scratch cards all over Rwanda and most places on Earth now for airtime. And so you can buy, in Rwanda's case, you could buy 25 cents worth of airtime all the way up to cards that have a $25 denomination. And so what we've been doing is looking at how this denomination is a proxy for socioeconomic status, and looking at basically how, using that to couple that with things like the census data that we have from Rwanda, and understanding what the distribution of wealth is in the country, and how these calling patterns are reflective of that. The other thing I wanted to focus on before I move forward is the fact, is the privacy implications again, right? So these are individuals now who did not sign a consent form. And originally, I thought this was going to be a real challenge to get it through CUIs, which is the IRB at MIT. But there's two things that made it a lot easier. One thing was that I have no phone numbers. I have anonymized IDs that are associated with a SIM card. And secondly, I'm not doing any data collection. This data already exists and sitting on a server, actually sitting on a bunch of servers underground in Kigali at the moment. So with those two caveats, this type of research becomes viable in an academic sense. So one of the students who's working with me at SFI right now is writing his thesis. Well, he's getting distracted in a lot of projects, but his thesis was how the structure of society and the stability of society, looking at this data over a long period of time, trying to identify cliques that form and cliques that basically dissolve. Are there particular characteristics of groups of people that are correlated with the stability of their relationships? So can we identify relationships that are going to be persistent? Can we identify groups of people that are going to basically stay a group for a long period of time, where a group is defined as individuals who communicate a lot with each other? So we've made less progress on that than I wanted to, but it was actually was inspired by a Nature paper Laszlo Barabashi wrote maybe 3 or 4 years ago, where he was basically asking the similar types of questions, but kind of getting at it in a different way. He was using data, I think, from on the order of about a year. But now we've got with 4 years of data and literally every phone call in the country, I think we can do a pretty good job at this.
What percentage of the total population does that represent?
So when we started, when the data started back in January of 2005, it was 200,000 people in Rwanda had cell phones. By the time the data ended, it was 1.4 million, which was about 15% of the country at the moment. And that number is, Africa is the fastest growing mobile phone market in the world. That number is rising almost exponentially, which is exciting. And
I would think it was a much higher percentage of kind of family unit level.
So if you look at number of phones per household,
yeah,
it's well over 50%. All right, so one of the reasons why I kind of keep focusing on the fact that this is every phone call in the country is that, in previous work, and Laszlo's as well, they've been working with operators that have less than 100% market share, generally less than 30% market share. And so we have a paper now basically showing how what the implications are when you're having that kind of sampling. So if you have all the data from a single operator, and that operator has 20% market share, what it turns out is you only have 4% of the edges, and less than 1% of the triangles. And so when you start wanting to kind of build something that diffuses over that graph, you get radically different dynamics than if you had the full graph. And Sune Lehman over in Barabashi's lab, he's been a big advocate of the fact that we need to get away from this idea of discrete community structure. When people talk about community structure in graphs, generally we assume that a node can only belong to one community. But that's kind of, it seems a bit silly when you think about it. If you think about your own social network, you're affiliated with your college, your college community, and then your Microsoft community, and maybe your high school community, your family community. So we've got a lot of different communities. But it turns out if you sample a social network down to something like 20%, you do get this kind of discrete community topology. But as you increase your sample size, you get overlapping communities. You get a densification of the graph. And so that's kind of what we're showing here is that the number of memberships increase as you increase sample size. What we're able to do is recreate all of the previous results that have been looking at processes that diffuse over a social network that has been previously published, at least when those authors were looking at a 20% graph, and we could recreate those dynamics when we sampled our graph at 20%. But then as we increased the sampling size, those dynamics they changed quite a bit. And so we've got a paper now in submission on talking about how those dynamics change, and the fact that when you want to think about constraining an epidemic, initially we focus on looking at the super spreaders, which are generally the hubs. But what we found is that actually membership for a large number of communities is 4 times more important than degree. Meaning it's more important to how many memberships you have with these different communities than simply the fact that you've got a high degree. All right, so that's.
Go back to those.
Yep.
Epidemic dynamics refers to
How something spreads over a graph.
Meaning what in this case?
Okay, in this case, you could think about it as information. I mean, right now we just used a simple SI model, so a susceptible infected model. This shouldn't be confused with disease per se, but this is what people have been using social graphs to as a proxy for how disease would diffuse.
But just to talk about the details of this particular study that you have in submission, what are you doing? You're saying, given this graph,
so
how could I go from one place in the graph to another?
No, what we do is we look at how many people you ultimately infect. So we run the simulation thousands of times. We take one individual out of the 1.4 million, we infect them, and then we watch this thing spread over time. And over a long period of time.
So you're taking this standard contagion model and applying it to the graph, and you interpreting the semantics of the arc as adjacency or a probability of contagiousness with or without the arc in place.
Yes.
Got it.
Yeah.
Okay. That's right.
Okay, so that's basically just talking about the implications of sampling.
But that model does allow for a jump without an arc, right?
You have to, yeah. You can't. You have to be connected in order to disseminate something in that case.
Well, have to be connected.
You have to, yeah. You have to have an edge.
Okay. One can imagine noisier models where you can, with much greater difficulty, catch something in ambience without the arc. Or look at
That's
the arc,
true.
Look at the arc as noisy, but when the arc is there, boom, you have a parameter change.
Yeah, I mean, there's all sorts of. I mean, what we wanted to do is do the absolute dead simplest model just to show the effect of membership versus degree. But as you increase the level of sophistication, you increase the realism, but then you add a bunch of other things that may make your point less clear. In this case, this is now another, or potentially clearer, but with more variables, so more susceptible to getting shot down by reviewers. So another study that we wanted to, or another question we wanted to ask, was about the effect of cities. And in this case, this is okay. So I should spend a little bit of time explaining this graph. These are all individuals who move from a rural area into the capital, and they move at 0. So they're spending the time in the rural area here, and then they move to the capital. And then the back movers, the individuals that end up moving back, are characterized by the solid line. And so you can start seeing. So this is the degree. This is their degree. So this is the number of people that they call in the rural area. And as they move to the capital, it goes down. But then the back movers, they move back after about 6 months, and then establish the same rural degree. And the same kind of goes for this is their capital degree. So it goes up when they move there, but then they never really fully integrate and then move back, and then it goes so that it goes low again. Whereas the people who permanently move are this dashed line here. So moving from a rural region to a capital, this is your capital degree. So it's more or less kind of static, and then it jumps and it keeps just kind of going up. So the idea here is, how does cities affect individuals? One notion is this hypothesis called differential selection, meaning that you behave differently. Individuals in the rural area who are behaving like an urban person, the more they behave like that urban person, the more they kind of get pulled into the capital. So that's kind of the theory of differential selection. They're different from their home environment, and that's what's driving them to move. And you can actually see, the individuals who do move are different. This is kind of the average rural degree, and the people who do move have have less integration, have less contacts within that rural area.
So this is behavior described as the way that they communicate with each other?
This is purely looking at the degree. So this is I guess, which is kind of a proxy for behavior, but this is the number of people these individuals called both in their home environment.
All communication pattern, and then you sort of divvy those up into sort of rural and urban. And
correct.
you say if you've got a communication pattern, you're rural, but you have a communication pattern that's closer to the
urban, then you're more likely to leave.
Okay.
And that is kind of the theory of differential selection. The other theory that's kind of has been in the literature for decades is this behavioral adaptation. So meaning you move to the city and suddenly then you behave more like an individual who is in a city. And so what we're trying to do is kind of figure out how much is differential selection, how much is behavioral adaptation, and it's still very much a work in progress, but we're seeing clear signs of both. And then the other thing that we're making progress on, but I think we're not quite there yet, is this idea of integration. So looking at how long does it take for individuals to integrate into these different communities, both these urban communities and these rural communities. And we're finding that it's a lot easier for people to integrate into an urban environment than a rural environment. And then there's fun other things about rural environments, whereas you may have lesser degree, but the tie strength is much greater. People in rural areas, they don't have as many contacts, but their relationships are stronger as measured by call volume. So there's some interesting dynamics going on in urban versus rural. And I've got another student at SFI now who's working on kind of building a generative model for the urban growth. And specifically, she's looking at Kibera, which is the largest slum in the world. It's just outside of Nairobi. And what we're able to do is look at how this slum is changing over time. We're inferring tribe by looking at what regions of Kenya individuals living in this area are calling. And you can start seeing the dynamics of of the kind of turnover of these different tribes moving in and out of these neighborhoods. And the hope here is that we can start parameterizing this in a way that we can quantify how the slum is growing over time and with what type of inhabitants. And this is important for people doing urban planning. I mean, these guys, they need to figure out where to put the next latrines, where to put the next pieces of infrastructure. Where's the slum going to go next? I mean, these slums in these developing world countries are very organic. They're ad hoc. They grow in kind of a very much an unsupervised manner. But I think and this is very much work in progress, but I think that it is looking like they have particular patterns in their dynamics that can be quantified. And if they can be quantified, we can get some insight into really what's going on.
So is that data for that stuff, that's also coming from the Rwanda data? Or?
This is coming from, Rwanda and Kenya. So actually, this slum is Kenya, which is 10 million. So I jumped ahead. But we're working with the city planners in Kigali. Kigali has their own sets of slums, but it's not the world's biggest slum. So we're basically applying these models, but we're using Kibera right now as well.
Okay.
So I hate the term universal law of human anything. But this is kind of, this was the name of the grant that we got, and so it's now the title of the slide. But the idea is looking at quantifying how mobility models scale over different people from different cultures and different continents. And so what Marta did earlier last year was basically parameterize a population's mobility in terms of a radius gyration. So it's kind of using a standard gravity model. She's able to find kind of the distribution of these radiuses. And what we're doing now is looking at what this distribution is across a variety of different regions, both in America, Latin America, South America, Africa, Europe, and seeing how, what holds as kind of commonality and what is different across these different regions. In terms of diffusion, not only do we have, so when we talk about CDR data, we not only have the communication data, but we also have this product adoption. So what products people are adopting over time, and especially in places like Kenya, like Rwanda, like the Dominican Republic, where there hasn't been as much mass marketing, simply because people live in more rural areas and are less connected. The importance of kind of how people hear about a product basically comes from your peers. And so what we found, and what's striking is this holds true both in the UK as well as in Kenya, as well as in the DR, is that if we want to start quantifying the probability that an individual adopts a particular product, you have a triad, so you have three people, A and B both adopted, and you want to know what the probability of C adopting is. It's significantly more, so meaning the probability of C adopting goes up significantly when the triad is closed, when A and B are friends. When A and B are friends, they exert more mutual influence over C than if they're not connected. And it's striking how that result seems to hold, again, across a wide range of markets and across a wide range of products. This is now kind of work that's veering towards developmental economics, but I think kind of should scale to a wide range of events. This is the implications of what happened in an earthquake back in February of 2008. And what you're seeing here, I mean, so the first thing is, well, you type in Rwanda earthquake and you see this massive spike, and then you find out that there was an earthquake in Nyamasheke region on February 3rd, and then you can start plotting what these are the behavior that's coming from cell towers in this particular region, and on the y-axis, this is outgoing minus incoming calls. So this is the net outgoing minus the net incoming, and you can see basically the cell towers were the time series started about here. And you generally have more outgoing than incoming until that earthquake happened. And then suddenly things changed dramatically. And this is a plot that literally we generated about 5 days ago. So there's no more kind of analysis beyond what you're seeing. But I think what it points to is an ability to start, ability to do things that Eric and I have spent the morning talking about, of being able to do surveillance, whether it's disease surveillance or flooding, or trying to detect flooding or crisis or market collapse. We have this data now on how people are communicating, how people are traveling, how people are sharing airtime, and the hope is that we can. Well, I can go to this next slide. We can start parameterizing people's reactions to these catastrophes, and in a way that we can use it for surveillance. Can we do something analogous to that Google, that Google flu trends paper, right? So I like the analogy that we could do something similar with CDR. And instead of people typing in search queries about sicknesses, we can identify key behaviors that are indicative of an outbreak. Signatures that are associated with people who are getting sick, or who have recently been flooded, or have recently been exposed to something like an earthquake. Do you have a question?
So you touched upon that the triad model, saying if there's a closed triad, then that affects the decision making of the third person. Have you applied that theory to the moving data that you had, who affects, who's the influencer, and where people move from urban areas to city?
No, we haven't. I mean, that's a good idea.
Because Michael Kearns at UPenn did some work in finding something to the effect of who influences things in social graphs. That's a very recent study. You should.
Right now, we're just looking at aggregate behavior. Okay. We're not trying to pull out individuals who are influencing more than others. Okay. But that probably, at some point we will do that. We're still just trying to get our head around kind of what the aggregate's looking at doing first. And so anyway, so there's a lot of questions that can be addressed, whether it's trying to identify. So I'm working with a group of epidemiologists at Imperial, and what they're trying to do is quantify how malaria how mobility affects malaria. So how people's movements around East Africa change the spread of that particular disease. And with Eric, we've been talking about trying to quantify people's reactions to something like cholera. Like when there's a cholera outbreak, and there have been dozens of cholera outbreaks during the time period where we're looking at this data, can we start characterizing how a region responds to something like that? And ideally, can we characterize the onset of a cholera outbreak? Can we see the events that leading up to a potential disease outbreak? If we can quantify that, then we can do some real good.
The idea is to not just model, but to intervene someday.
Yeah. So if you can close the loop, if you can identify when a disaster is about to happen, there's a lot of organizations, both governmental and non-governmental, that would be very eager to help out. Josh and I. So Josh is a student at Berkeley. He just arrived in Kigali today, and we're conducting a phone study, where we're surveying people and asking them a variety of both socioeconomic questions, but also about what their livelihood is dependent on and whether or not they've been involved in an economic crash of some sort or been touched that way, with the idea of trying to figure out how behavior is correlated with things like market prices. All right, so now from a million Rwandans, we've got essentially the same data for Kenya. Now it's 10 million mobile phone subscribers in Kenya, but we've got an additional edge type. Instead of just communication and airtime sharing, we've got actually how people are sending and receiving money across these different regions. It's a product called M-Pesa, which is kind of mobile money in Kiswahili. And what M-Pesa has enabled is a variety of really interesting applications that lie on top of it. So I mentioned earlier this company, TextEagle, based in Nairobi. And what it simply does is enables people to earn small amounts of money on their phone by completing really simple tasks for corporations who pay them generally in airtime or M-Pesa. Tasks are things like transcription, translation, image tagging, surveys. We've got right now we've got something like 15 million subscribers who now have phones where they can start earning money. And the question is coming up with enough tasks to meet the demand. I mean, we soft launched in February and with a series of translation tasks, and we had to shut the service down after something like 6 hours because we ran out of Kikuyu and Luo tasks. We introduced the service to some taxi cab drivers and some high school students, and just within hours we had thousands of users. There's a huge demand for being able to start making money on your phone by completing work, and it's just a question of figuring out how to get enough tasks. It's pretty exciting. So if people in this room have an idea about how crowdsourcing can, what particular paid tasks can be done on a handset, and it's important to think that these are not kind of smartphones. I mean, this is a handset from the handset that you had 10 years ago. So initially we deployed via SMS, but now we've gone to USSD, which is so SMS is to USSD what email is to Telnet. So USSD is this kind of persistent sessions-based GSM protocol that works on literally every single one of the 4 billion GSM phones on the planet today. So it's a fantastic opportunity, I think, and it's a great protocol. But the problem with USSD is that you have to be an operator in order to deploy a USSD service. And so this is done this is basically done in-house with these operators. So that's, and then I put mechanism design. So this is an example of trying to figure out what the kind of incentive and reward structure should be so that you can get this work done. When we initially launched, I think we were probably paying people too much. People were earning upwards of $3 an hour. And that was that. I think when we redo this again, I think really what we're going to try to do is cap how much the daily amount you can earn is to maybe $1 or even less, so that we get a wider selection of people who are completing these tasks. So from those 10 million East Africans, this is now 100 million individuals in the UK. This is a graph actually of, it's a social network now of 250 million unique phone numbers, 12 billion edges, and we've got things like the nodes are characterized by region, by product adoption, and the edges have a time and duration associated with them. This represents virtually every landline phone call on about 80% of the mobile phones for the month of August of 2005. So it's a very large graph. And I'm at the Santa Fe Institute now, and so one of the job requirements is to show straight lines on log plots, and this is a particularly good straight line. This shows calls made for, in this case, this is August 19th, 2005, and what you're seeing is 10 million people in the UK made one call. 1 million people made 10 calls. 100,000 people made 100 calls. And it just keeps going down and down. And the thing that one of the things that initially gets pointed out is who are these people who are making 100,000 phone calls in that particular day? And this seems to be true across these different data sets. It's a true power law all the way out to the tail. And these are clearly not human. And actually, we have a little. We're trying to build a little classifier that tries to pull out what machine-related properties. If you behave like a machine, we're not going to count you anymore. But this is the unfiltered unfiltered graph. And the thing that's striking for me, I think, is just the fact that out of the behavior of hundreds of millions of idiosyncratic individuals, every single day, this is a straight line. But the interesting thing is that it's the straight line, the slope of the line, the exponent of the power law changes with the day of the week. So you have like a Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. And that calls out, and then you have a mirrored you have a mirrored exponent for calls received. So there's something fundamental about what's going on with the dynamics there that I think is interesting. We've been doing a little bit of work at just looking at how distance affects probability of communication. So this idea of propinquity, it's this notion, the fact that you're much more likely to be friends with people who are proximate to you. And what we've done is, this is kind of similar to a PNAS paper by David Levin-Knoll, where he took a LiveJournal data set and looked at the probability that individuals would link based on zip codes. And this is what we've been able to do, is recreate that distribution that he found for LiveJournal with the UK. And it looks like Rwanda and the DR follow a similar distribution as well.
We did a similar graph for messenger data for the month of June 2006 of messenger communications. However, we did an additional study. How often do you talk to somebody, given that you've talked to them before they're on your graph, and it goes up with distance?
It goes up with distance.
Yeah. So it basically is, you see people locally, personally, but you use messenger to talk to people who are far away.
So your low weight ties are your proximate ones.
Right.
Yeah. We should do that too.
Yeah.
So in any case, we're seeing similar. I mean, and that's kind of a neat. That's a neat finding, right? Whether it's instant messenger data, whether it's LiveJournal data, whether it's communication data from England, from the middle of a village in Rwanda, like getting the same types of distributions repeatedly across different types of communication medium, across very different types of demographics. I think there's something interesting there. But it gets more interesting once we have that outcome of interest. So looking at the outcome of interest for this slide is the multiple index of deprivation, which is an aggregate score that's associated with access to healthcare, education levels, and average income. And this is for the UK. And so what we're doing here is we're testing the Granovetter hypothesis, the strength of weak ties, right? So Granovetter many years ago has kind of has theorized that it's going to be that acquaintance that's going to get you your next job. It's not your best friend who's going to be able to kind of push you forward socioeconomically, but rather it's these weaker ties. And what we've done is we've looked at diversity. So again, diversity now is well, in this case, this was a Shannon entropy metric, but we've also used Simpson metric for diversity, and it's more or less the same. It's an idea of how much entropy is in an egocentric graph based on the geography that they're calling. And what's striking is that socioeconomic status, it's really not that correlated with your degree or your call volume. Meaning it's not the number of friends you have or how much time you spend on the phone, but rather it's this diversity score. It's whether you have you have contacts in a wide range of areas, and so this is a pretty amazingly strong correlation, especially in the social sciences, where we're explaining more than half of the variance in a group of people that numbers 50 million. So this is a major result. But the controversy right now is figuring out what's really driving this, because there's another theory from Burt about structural holes and constraint. And I could spend a little bit of detail about talking about that, but basically, essentially, it's just if your friends are friends. So if you have an insular group, what Burt theorized was that that's going to constrain you. That's going to mean that it's harder for you to change. And that constraint is going to affect your socioeconomic status. Whereas if you have a lot of holes in your system, meaning if you got a lot of friends in a lot of different places, then basically you're going to be better off. And so you could see how there's parallels there with diversity. And so trying to figure out what's really the driving force is still an open question. But But at the end of the day, we're able to start validating these types of theories because we have these amazing data sets. And it's not just all the communication graph, but it's also through the UK Civil Service, they've done very detailed studies about the socioeconomic status of all these regions in the UK. And so it's really when combining these two things where we can get some interesting results. Yeah.
Building services on top of that now to address these issues based on this data? Are governments investing?
Well, that would be the ultimate goal. So to date, no. And one of the reasons is I can't really advocate them to do that because what we haven't done is talked about causality. What we've only done is we talked about correlation. If I can establish causality, then I can actually make a case to the government saying, like, look, this is a particular policy you need to start adopting. You need to create these longer edge ties across the nation and improve everyone's socioeconomic status. I can't make that case to the government yet because I don't know whether or not which direction it goes. And my guess is it's going both ways, right? So people who have have higher diversity, they're going to be exposed to more opportunities, and so that's going to drive socioeconomic status up. But the wealthy individuals, by the nature of being wealthy, will have these longer ties as well. And so trying to figure out which way causality works is very much an open question. Okay, and then I'm going to wrap it up now. I mean, with the billions, and this is. I'm working with, like I said, dozens of mobile phone operators from around the world, and it allows us to ask a variety of really interesting questions, whether it's looking at the dynamics of relations between nation states, and looking at how culture affects things, disease outbreak warnings, etc. So to wrap it up, I mean, I've talked about where n equals 100, I'm starting to infer the friendship graph based on these behavioral signatures. When n is 1,000, trying to figure out what kind of relationships people have, friends, office workers, colleagues, based on their communication behavior. N equals 10,000, this is the random sample, 10,000 of individuals across America, and learning basically what random sampling can do for us. So the 100,000 criminals in Philly, trying to figure out whether or not there is such a thing as a crime wave and whether or not crime is contagious. To 1 million people, where we're looking at how the effect of urbanization affects people's support social networks, trying to understand how disease and disease dynamics interplay with things like mobility and communication. 10 million people, this is looking at how resources flow through the network, economic resources, and then this platform, Text Eagle, that enables people to earn money on their phone. Then 100 million, trying to validate for, I believe, the first time this theory of Granovetter had about whether or not these weak ties really are strong economically. And then now into the billions, where it's possible to start comparing across cultures and across continents. And it is striking the similarities that we're initially finding. I mean, so this study with Marta, it seems like that people in the Dominican Republic move in similar patterns to the way people move around Rwanda, which bears striking parallels to how people move around San Francisco and LA and Belgium. There's particular types of information that spread over Greater London with exactly the same dynamics as it spreads through a village in Kenya. So we're at a time now where we can almost, well, I'm still pushing a little bit against it, but we can almost start talking about universal laws of human behavior. But I think kind of the bigger question, in fact, like kind of the ultimate open question here is really an engineering question. Like once we've got all this data, once we've got all these insights, once we've built this model of a system, how can we use these insights and use this data to actively improve people's lives? Because I'm as big a fan as anyone about plotting the aggregate behavior of 100 million people on a log plot and fitting a distribution and then raising up your arms and yelling eureka and claiming that you found a new law of human behavior. That's the easy part. I think that fundamentally the harder part is trying to figure out a way that we can use this data to improve the lives and better both the lives of the billions of people who are generating this data continuously and the societies in which they live. And for that, it's no longer the social scientists who want to be validating theories or the physicists who want to start messing with the degree distributions. But now is the time for the engineers. Now is the time for the applications. And I think we have the potential to really make a difference here. I mean, this could be extremely high impact work. And so I think it's an exciting space to play in. And I'm playing in it with a variety of people. And I'm welcome to continue to add to this list if other people are interested. So with that, I'll open it up for questions. Thanks.
Questions? Should I give out my cell phone number for the people out in the in video land? You can call me on my cell phone. Questions? It's for CDR, land here.
Yeah.
Any comments, questions? Yes.
Are you going to get any of this data like real time, or are you always getting past chunks of data?
Getting real-time data is possible, but I haven't tried. I mean, to justify getting real-time data, we'd have to propose something like what Eric was talking about earlier about interventions. At the moment, I can't make the case that I have any intervention or even the ability to detect something that the operator or the government would care about. But when we do, there's no technical reason why that's impossible. We should, and that would be the ultimate goal, would be build a little filter on the real-time CDR to start flagging regions that look like they might have just had a disease outbreak.
Yeah, even a little bit out of phase, and with bulk uploads.
Yeah.
Yeah.
So are you going to take the same models and apply it to other ways of communication, like Eric said, MSN Messenger, Facebook messages, and Twitter exchanges, and things? Because that's a real-time field that's open, and you can just grab data out of there. Because a lot of these models should be applicable regardless to the mode of communication, right? There's relationships in every graph.
Yeah.
And you should be able to take something in one graph and see how it applies to the other one.
Yeah.
Do you have plans to do something with that?
I'd like to. I mean, to be honest, I've got more data that I'm drowning in data, and I earlier in my life I was a data junkie. It just was there's never enough data. I always wanted more, and I'm kind of reconsidering that position, and I'm really trying to be kind of more focused on questions that you want to address rather than just trying to build the biggest social network that has ever existed. But that question appeals to me as well. So yeah, I mean, I'd love to be able to couple different types of data sets together, especially if you can legitimately couple them. If you know the hashed ID of the phone number, you know the hashed ID of the messenger account, you know the hashed ID of the bank account. This is I'm collaborating with people who have a bunch of Bank of America data, and so but there's a lot of privacy implications obviously associated with coupling these different data sets.
So I said step out for a minute, so I may have missed this part, but when you said that you started working with Kenya as well, some of their mobile stuff, is that right?
Mm-hmm.
So are you seeing sort of the same kinds of relationships with the call structures? I don't know, are you getting data with the M-Pesa? I'm just curious about sort of, is there symmetry or similarity in the networks between the call structure stuff and the in-banking kind of relationships, or are you getting?
This is early stages. I can tell you kind of what things like the degree distribution looks like for these different networks, and also the airtime sharing. I mean, there's kind of a lot of there's SMS, there's communication, there's airtime, and there's M-Pesa. And as you go down that line, you get a sparser and sparser graph. And typically it seems to be correlated with volume. So if there's a lot of volume between a dyad, you're much more likely to have that M-Pesa transaction. But we're on early stages, and I really can't. I'm not comfortable saying more than that until we really kind of stare at the data more.
So,
Leo?
I was wondering if you're already doing anything in terms of mass intervention, like providing people with access to information about their own behavior on the web or on the phone, and try to close the loop.
That would be the hope. I mean, the first thing is trying to establish a piece of information that that would be relevant to these individuals. And I think something like the fact that there's a potential disease outbreak would be a pretty good one. The other intervention, which is less of an experiment and more of a commercial entity, is this idea of improving people's socioeconomic status by providing them work, so giving them income based on them doing these tasks, and then seeing how that changes their behavior over time. And I mean, that's nice because that really does. I mean, we've got the 15 million people in East Africa who participating in that. So that's about as big of an intervention as I can imagine.
What sort of restrictions do you have to work under when you're working with these data sets? I mean, do you have to go to these locations and work in these locations, and you cannot take the data?
Well, taking the data out is generally okay under major constraints, but typically, I mean, a lot of this data, I've spent weeks, literally weeks, in underground basements in Kigali, in Nairobi. And it's a surreal experience, actually. You're in this giant server farm that's just, because you're on the equator and you're being blasted by air conditioning, and then you take the elevator up and you walk out the door and you're in the middle of Africa. But yeah, I mean, to deal with that, to get access to this data, I have to work very intimately with the operators. I mean, and the operators are interested because we're providing them services like TextEagle, and then also insight into the dynamics of their subscriber base. And at the end of the day, they don't have the computational resources nor the human resources to analyze this type of data, and so that's kind of the value proposition there. And so I can take it out. It has to, for obvious reasons, be encrypted. There can't be any phone numbers, anything that can identify an individual. And I want that for my own protection as well as for the privacy protection. The last thing I want is to be indicted and have this data come out and be going into a court case or something. So it needs to be de-identified in a very rigorous way. And some operators are more paranoid about that than other operators. But for me, that's kind of a mandatory thing.
But taking out the phone numbers is one thing, but you have a lot of information. Even if you can't identify, if you have someone's phone number, clearly you can identify them pretty easily. But with the type of data you have, you could probably identify a lot of these people even without the phone number.
That's possible. I hope not. I have to make the case to the IRB that that's not possible. But I think that's, I don't know.
Grad student proving that it is possible.
Yeah, so we were talking at lunch, this Kleinberg paper of showing, just looking at topology alone, you can start cracking some of this stuff. To be honest, I'm less worried about those attacks, because those type of attacks, they let you find yourself and maybe figure out who your friends are friends with, but it doesn't go beyond that. So my real concern is making sure that, and this goes to the fact of just being able to, ideally, I'd like to release some of this data to the academic community. That's the biggest contribution of my PhD was not these little generative models of MIT behavior, but rather it was releasing that data set online. And it's generated literally hundreds of journal publications. It's been downloaded thousands of times. It's been a pretty big contribution. Having this type of data, getting it out there in a way that's ethical would I think be a phenomenal contribution. But the problem is trying to figure out a way to do that while preserving privacy. And at the moment, I don't know the right answer to how to do that.
And what sort of volume in terms of terabytes are you dealing with the largest data sets here?
The largest data sets, these things compress phenomenally well. But uncompressed, we're talking maybe half a petabyte.
Thanks very much.